Hello everyone. Today we will be presenting our topic for DSIP Internal Assessment 2, that is digital image compression using discrete cosine transform. I am Bharat and my other groupmate is Roshan. Uh, let's begin by what is digital image compression. It is a method that is used to decrease the size of an image by either removing redundant or irrelevant information. One of the most commonly used techniques for image compression is the DCT or discrete cosine transform, uh, which changes an image from the spatial domain to the frequency domain, allowing for the image to be compressed by removing high frequency components that are not important for the human perception. The DCT method is utilized in many places in various images and video compression standards, such as the JPEG, MPEG, and H.264, which is also .mp4. This presentation will explain how DCT-based image compression works and how it can be implemented using popular scientific computing libraries such as NumPy, SciPy, Scikit-Image, and many others. Okay, let's move on to discrete cosine transform (DCT). It is a lossy compression technique which is used to convert an image from the spatial domain to the frequency domain, as I said. And this technique divides the image into small blocks of pixels, such as 8 cross 8 or 16 cross 16, and uh, those are transformed using the DCT. And the transformation produces a set of frequency coefficients that represent the image's energy at different frequencies. To reduce the number of bits required to store these coefficients, they are quantized by rounding them off to smaller set of values. The quantized coefficients are then compressed using techniques such as run length encoding or Huffman encoding. And during decompression, this process is reversed, and the quantized coefficients are dequantized and transformed back into the spatial domain using the inverse DCT. The result is an approximate reconstruction of the original image that has been compressed to a smaller size with some loss of quality, but a much smaller size. The level of compression and loss of quality can be adjusted by changing the quantization parameters. I'll hand it off to Roshan to explain how our program works.
Thank you, Bharat. Now I'm going to talk about applications of DCT. It can be used in digital photography. DCT-based compression is used to store high-resolution images on digital cameras, mobile phones, and other devices with limited storage capacity. Second, it is used for video compression. DCT-based compression is used in popular video codecs such as MPEG and H.264 to compress video frames into a smaller size, allowing for efficient transmission and storage of video content. Like it is also used for medical imaging. DCT-based compression is used in medical imaging applications to compress large medical images such as X-rays, CT scans, and MRI scans, enabling faster transmission and storage of medical data. It is also used in web-based applications. Is used in web-based applications to reduce the size of images, allowing for faster loading times and improved user experience. Now we are going to move with the implementation, how the code actually works. So here we have used multiple libraries. The first library, the SK image library, is used to read and write images and into multiple formats. The second library is used for linear algebra. The third library is the Fourier transform library from SciPy. It is used for doing DCT and its inverse. And the last is the matplotlib lib.pyplot, which is used to plot the quantization of the images. Here we take the input image, that is cat.gpt, and we give it a quality that is good. Then it's given a parameter to compress this image, and here we use the quantization, and the p is the parameter of how good the image should be. The lower it is, it's great, and the higher it is, it gets usable. Then we do the metrics for the DCT, and we apply the DCT code for the and then we separate into eight into eight blocks for the three channels, that is red, green, and blue. For because it is a colored image, it requires three channels. Then here the blocks get the DCT to D, and then the inverse of that, and then it prints the image. So it gives the percentage of how the DCT, or how much the coefficients are kept of the DCT, and then again gives the values. It prints the values for the different colors of the blocks. So for the running of the code, let me start the code. So here the code is compressing this image, and it gives the base DCT matrix and the base linear quantization matrix for this, and then it does for the 8 into 8 blocks for red, green, and blue, and then it only keeps 5.031% of the DCT coefficients. And here are the results of the images using matplotlib. As you can see, the images are the image here is pretty high resolution, and here it loses some of the pixels of the image to make it low quality. Also, for comparing the sizes of the image, so for the comparison of the two images in sizes, here is the code for that. Then compare.py. So the compression percentage is 79.41%. So here the image here and here has lost about 79.41 percentage in size. Thank you for your time.